let's kind of start here. Hanson, you just let me know if you if it's not working for you, and then we'll make a pause here. Okay, right there. Okay, here's what I'm going to start with, and this is going to be a little bit different than yours. You're not going to have this outline on yours. Oops,
Okay.
sorry.
Non-meeting?
Okay, so this next slide here isn't going to be on yours, but it'll be on mine. It has an outline of what we're going to be doing here today, and then we'll start clicking through all of these. Goals today, I want to do a section 6.4. I want to review a couple things from that. That was the stuff we did last week. It was about rectangles, and we talked about parallelograms and all that. So I want to do a quick review of that. We had some properties last week, like the definition of rectangle. We had some theorems, that was 613, 614, about the diagonals of a rectangle. And then what we went into on Friday was some new properties, which was the sort of 6.5, and it talked about a rhombus, and we went through a couple properties about a rhombus. We went, I think, 6.15, 6.16, and that's where we stopped. And there were some classes, they got one more slide than you. They talked about squares. But the goal today is, after we review these, I do want to review these properties in case you were gone, because some people like to have those written down. And I'll make sure it's on the website tonight and stuff. I don't think I updated it for Friday, so I'll have to go through that and have that PowerPoint. But I want to make sure that that's something that you get your notes on. And then we'll do a couple of problems right after we get through that to kind of review to see how well you're going to do here. And then we're going to get to our new stuff, which is about squares today. And I want to talk about, the definition of a square, do some problems on that, and then get through a bunch of actual properties about rhombi and squares in general, which are 4. I don't know how far we'll get today. That's kind of the idea. This is where I want to go. These properties are very short. The good thing is, on the PowerPoint that I'm doing today, on this this Nearpod idea, I'll have all the proofs in there. So if you're clicking through, you can write it all down. So you don't have to wait for me to actually do the proof. And we'll do a couple examples after we're done. Okay? Questions at all with any of that? Okay, so it's tall order. We have a lot of stuff to get through today. I think we're going to be fine. All right, let's jump right in. Okay, let's do our section 6.4 stuff. So it should appear on your Nearpod, correct? Okay, good. All right, here we go. Rectangles. The big thing we talked about with rectangles, it is a quad, it is a parallelogram, but what makes a rectangle special is that it has 4 right angles in it. 4 right angles on an actual rectangle. And this is the picture that I've been showing all week. We even did it almost every day last week. They have right angles in the corners. There's 2 properties we talked about last week with a rectangle. Okay, 613, which is called the diagonals of a rhombus, or diagonals of a rectangle, I should say, where they're actually the same length. So these sticks on this picture, JL and NK, the sticks are actually the same length. Now, the big thing we talked about on Friday was that the angles don't necessarily have to be equal in the corners. Like these angles, they don't have to be the same angle. It doesn't have to be 45 and 45. One could be 30, the other one could be 60. All I know is that they have to make 90 in the corner. Okay? Now I know that certain angles can hopscotch around, but they're not exactly like 45s. That's something that we'll talk about maybe at the end of the day today. That's 613. It was called the diagonals of a rectangle. Then we did 614 last week, which was the converse, where you start with the diagonals being equal and you show that it had to be a rectangle. So if I gave you this picture and you knew that these were the same length, then it forces the angles in the corners to be right. That was something we did at the very end of last week. And I want to make sure that we're comfortable with that. You should have those 2 theorems already, correct?
Yes.
I don't even think those weren't even Friday's. Friday's stuff is all the new stuff past that. 615, 616. Okay, new stuff that we had Friday. This is the stuff we introduced that was new. Okay, we talked about the definition of a rhombus on Friday. So if you were not here, a rhombus is a parallelogram, so it has parallel walls, but I should click, sorry. Totally forgot to click. Okay. A rhombus is a parallelogram that has 4 congruent sides. That's it. That's the whole difference. It has 4 congruent sides. So this is the picture that you should be seeing on your Chromebook right now that's popped up on the Nearpod, right? Nope.
Nope.
Should be.
Yeah.
No. Yeah, it's already there.
Okay.
No, it hasn't.
Oh, wait.
Yeah, it is. It looks like the same slide that we just showed, but it has different properties. Sorry, it's very subtle. But a rhombus has four congruent walls. Okay. Now the new properties, and these are the two that we had right at the end of the day on Friday. Okay. We had 615, which talked about that if a parallelogram is a rhombus. So if this is truly a rhombus, then the diagonals in the middle are actually perpendicular to each other. So the middle angles in the very center of the picture have to be 90s. This property is unique to a rhombus. This doesn't happen in a rectangle. It doesn't. You won't have 90s in the middle on a rectangle. It only happens on a rhombus because the walls are equal. Okay? And why this is important is because if that's 90, then all four of these in the middle are 90, so you have a bunch of right triangles. And that's one of the new properties we'll look at today. I think on Friday we even reviewed how to do a problem with like Pythagorean theorem. We did a problem with SOHCAHTOA. So those are things we're going to try to review more and more. They're not going away. It's something that we have to know how to do with Pythagorean theorem, like a squared plus b squared equals c squared. Or SOHCAHTOA, like sine, cosine, and tangent, knowing what those mean and how to use them on a calculator. That's something we're going to try to do more and more of. So just be aware of that. We're going to start reviewing that more and more. Okay, the last property we had on Friday, and I think this is like one of the last slides we got to, and then we did a couple example problems, where if you have a rhombus, then the diagonals, instead of just being perpendicular in the middle, they actually cut the opposite corners in perfect pieces, and this is the last slide I think you guys got on Friday. The angles in the corners are equal. So I even color coded them. So like angle 1 and 2 up here, and 3 and 4 down here, those angles are all the same angles. So 1, 2, 3, and 4 are all the same. So if somebody just makes up a number, just throw out a number, 8. Okay, if this is 8 degrees, then 2 is 8 degrees, 3 is 8 degrees, and 4 is 8 degrees. They're actually all the same. So that makes this angle 16 and this angle 16 in the corner if you actually add the 8s together. And if I have the 16s, then I can find the angles next to it, because the angles next to it would have to be 164, because that adds a 16 to make 180. And if that's a 164, then we can split that in half and make that 82 for each of these. That'd be your 164s. Questions, comments? Okay, now as I promised, as we got done with this review, I want to do at least one problem here today that gives us kind of back in the swing of things to see if we can actually do this. So the next slide I'm going to show you, and it won't appear up here, I'm going to leave these up here so you can use these properties. The next slide that will be on your Chromebook is an example problem. Okay, I want to see if you can solve it. Now, the problem is, if the picture gets cut off, you can do the little drop-down menu, and it will show you what the question is. But it's not going to appear up here. I'm going to see if it'll work out a little bit better than we did on Friday. So here we go. So the problem should be appearing. You can, if you look at the top of the question, it has, what the question is. They ask for AC on the picture. Ask for AC. They give you a couple of parts of it. And if you can't see the lettering, you can hit that little blue button in the upper left corner, and it will actually show you the full picture. Like it'll get rid of that question. But you need to try to put these in your notes. So if you have your notes open on the side, let's see if you can solve this and you can write your answer in there. Try to avoid drawing anything that won't help you. Don't draw like pretty pictures on it. Just try to solve for X and let's see what you come up with. Shoot. Susan, did you put your name as a smiley face today? You put your name as a smiley face today.
I'm fine.
See if you can submit your answer. Let's see if we can come up with it. Again, I don't want to put it up here, so I'm going to just people use it to actually submit your answer. See if you can solve it. Again, you can write it in there with your actual trackpad, like actually drawing it. You can even use the text box. Some people like to type it in using text instead. But once you have your answer and you've actually solved it, let's see if you can actually submit your answer. Let's see if this works. So get a little more practice with this website and see if we can get better at it. Okay, I left the properties on the board to help you out, in case you don't remember what the properties are. I don't know how they work. Alright, it's still a parallelogram, so it still has the following properties of a parallelogram. Got a submission. You can make an adjustment and submit again if you need to.
Don't know that word.
How do you go at that?
How do you get to? They go back. This one?
There you go. Keep going. Hold it down.
Make it dirty.
There you go.
Orange.
You're good. There you go.
Yeah, man.
Alright, now here's the beauty of why I picked this. Okay? Here's why I like this website. I can share people's answers. I think this is really cool. This is what I saw. This is just one. Obviously, this is steps. I just like the penmanship that are involved here. Okay? She showed that the two sticks, AP and CP, those are the parts that were given to you. Okay? And she found X, and she showed, you know, kind of what X was. Now, here's my question. This is for Steph. Did you answer the question, though? What did the question ask for?
Find AC.
Yeah, find AC. You found X. I'll agree. Your X was fine. It was 5. But you had to plug it back into the question. So if you plug the 5 back into her problem that you're looking at, then you can find what the length of AC is. So you have to plug that 5 back into x's. Now, here's one of the answers I saw that is not correct. Sorry, I'm not picking on anybody in particular. Let's see, where is that? Okay, this is one that I saw, and I'm not picking on anyone in particular, and I'm picking this one because it doesn't have a name on it. All right. There's a 10 in the corner. AC is not 10. Here's why. X is 5. I agree with that. But you can't just double the 5 and make the whole stick. You had to take the 5 and plug it back in, and this is the problem we should have had, or this is the answer we should have had. Now, AC should have been 28. Because when you take the 5, you plug it back in, you would have got each stick would have been 14, and it makes a total of 28 for AC. Okay, but it was just one of those things I wanted to show you kind of what we can do with it. And I thought this was just kind of cool. All right, let's move on. Question?
I got 10, because
Yeah.
I did have.
I never got 10. Just a 5 you got 2.
Wasn't 9 plus 5?
I never got 10. I did that every time I did.
It was, I was.
Sure, you made sure I knew.
All right.
Mr.
Oh
Ward.
my.
Question? Yes. Okay, all right, here we go. Let's keep going. Okay, today, let's do a quick review of a square. Now, most people know what a square is. We had this, 2 weeks ago, what a square is, when we did the waterfall chart on the definitions of polygons. But I thought this is important enough we need to rediscover what a square is in case you don't understand what it is. Okay, square is a parallelogram with 4 right angles and 4 congruent sides. It's got everything. It is a parallelogram, so it has to be a 4-sided figure. Opposite walls are parallel. Has 4 right angles and 4 congruent sides. Now, the picture, here it is. This is what most people associate with the square. It's got everything. It's got the equal wall, it's got the equal angles. This picture also has a different name to it. Anyone know what we could call a square? Something we haven't talked about in a long time. Starts with the letter R. Say, it is a regular quad. Perfect. Nailed it. It is a regular quad. The word regular means everything is the same. All the walls, all the angles. It's a regular quad. That is the perfect name for that object. It is also known as, a square can also be known as a rhombus. It is also known as a rectangle. It is also known as a parallelogram. And it is a quad in general. You can call it any of those names, but I think the best name is the one you just nailed me, was that it is a regular quad. Okay, now notation. This is what the book usually does. They usually write the word square, they put the 4 letters. That's the same drill we always do, but here's the extra thing we can add on. Since it is still a parallelogram, you are still allowed to draw a picture. You draw the mock picture out in front, you make the markings on the picture, then you put the 4 letters behind it, and you can put them in any order you want, as long as you spin in a circle. So if you start with the letter C, I just picked out at random, and you go in a circle, that is still the name of it. So CDAB or CBAD, I don't care which direction you go. Okay, but you can draw the mock picture and put the letters after it. These things mean the same thing to me. I don't care if you draw the picture or if you write the word square in front of it. The reason why you're doing that, you have to identify the object. Nothing's easier to identify square than seeing all those marks. Seeing all those things right there. That makes it a square, not just a rectangle. Because rectangles would have 2 other walls that are different in length. Questions with the square itself. We haven't seen that one for a while. I called it a review, but I mean, that was 2 weeks ago when we saw that word. All right, we have new problems today, new properties that I want to get to. I want to make sure that we're comfortable with all this stuff, though. Okay, all right. So, even though my slide up here says new notes, I have a couple problems I'd like you to try. Okay, the little drop-down menu will show you a problem, but I want to see how well you can do, and I'm going to put it up on my. how well you can do here. Again, you can write in your answers, you can solve, but again, hopefully you're using some basic common sense about the picture. It is a parallelogram. It is some form of a rhombus, so you know that. Because we're talking about rhombi and squares, but it is a rhombus of some form. And I like you to find a certain angle. But the picture you're looking at is a rhombus. See if you can go back and use some of the properties we previously discussed. In fact, I'm going to put those properties back up here in case you don't remember what those properties are about rhombi. We're going to get your answer. Don't be afraid to hit the submit button in the bottom corner and see if you guys are kind of paying attention to some of the properties we have. Remember, hit your submit button once you have your answers. Write them in there. You can type it, you can write it. I want to see if you can find a solution to that problem. Again, you might need to use a secondary calculator if you don't have the calculator app installed. Every Chromebook should have installed. It's default here from the school, but if it won't pop up for you, you got to use a secondary calculator. I don't think you need one, but you might. You want to double check your answer, make sure it's correct. Wait, now just to select you here. See, hopefully you hit submit. Again, if you have terrible penmanship, you can always use the text box. What?
Don't cheat.
Alright, I'm going to share an answer here. Anyone got it submitted? Here you go. I like it. Okay, let's talk about why. Why is it 32? Why is your angle 32 in that corner?
Try to do a bisector.
Yeah, it's an angle bisector. It's actually this, right here. You actually bisected the angle. So when they told you that one of the angles, now I know I don't have the same letters as you guys, but when they said that this whole angle down here in the corner was 64, then I know a lot of you put the 64 in the other corner, but they wanted only half of it. They wanted that angle right there. So you just had to take the 64, cut it in half, so it's 32. And that was CAB, I think that's what they wanted. Okay. But that's one of your properties. It's literally this property right here. You're bisecting the angles in the corners. So the angles are cut in half. That's what bisecting means. I had some Most people had that. I had a couple people just put 64. The opposite corner is 64, but I didn't want the whole corner. I wanted just a chunk of it, half of it. So, and again, you can do that because of this property. We got angles in half. Okay, let's go to the next one. That was very good. I was impressed by the answers that were shown. Okay, all right. Next one. Here we go. Okay, this one's based on vocab. You have vocab at the bottom. You have to drag it to the blank spot and then hit submit. So it's checking on your vocab skills. See if you were paying attention. I believe it even tells you if you're right or wrong once you hit submit. Okay, can somebody just read off the sentence that you just submitted? Somebody just raise your hand, please. Haley, what again?
If a parallelogram is a rhombus, then its diagonals are perpendicular.
Boom. Right there. It's right in front of you. If a parallelogram is a rhombus, then the diagonals are perpendicular. It's testing your vocab words, seeing if you know what they mean. Okay? You had to have the parallelogram, and then it forced it to be a rhombus, and that forces the diagonals to be perpendicular to each other. Okay? Alright, let's move on. New notes today. Alright, new notes. We have a couple new properties today. I know we're not going to get through all of them today. That's fine. We'll continue on tomorrow. Once we're through these basic notes, and again, the PowerPoint I'm going to show you does have all the steps, so in case you're writing them down, I do have all the proofs written out for you, because I know some people like to see the proof already written out, so they don't have to wait for me to write it. But we have 4 theorems here. Now again, we may not get to all of them today. We'll get through maybe a couple of them, because I know we're short on time today. Okay, here it is. 617. Okay, I know that there's a lot of words in there. If you don't want to write the full-on proof, that's fine. I put it in there in case you want to. Some people like to know what it is. They don't want to wait for me to do it. So, 617, here it is. If a diagonal of a parallelogram are perpendicular, then it forces that parallelogram to actually be a rhombus. So here's the picture. So if we start with the fact that this picture actually has perpendicular angles in the middle, right here, boom, perpendicular, then it forces that picture to actually be a rhombus in the end. That all 4 of these walls would actually be equal to each other. That's what we're going to try to show in the end, that all 4 walls, AB, BC, CD, and AD, are all the same. Now, I have all the steps for you on the actual PowerPoint, in case you're clicking through and you want to see it. I'm all there in case you want to know what we're going to do here, but the proof is pretty straightforward. Now, I do have all the steps, but I'm just going to show you, okay? All right, so here's my question. If we know that if this angle is perpendicular, what can you tell me about the ones around it? They're all 90s, because all these angles are straight, so they all have to be 90. That was one of our theorems we had way back in chapter 2. If you have 2 angles that are adjacent, and they make, they're supplementary, and one of them's 90, then the other one's 90. It was a long, long, long time ago. So we have a bunch of 90-degree angles in the middle. Now, the other things, if you're looking at this is still a parallelogram. They gave me that fact in the very beginning. They gave me the fact, other than having perpendicular angles in the middle. They said that it's still a parallelogram. Well, one of our theorems we had was theorem 6-7, stating that the diagonals bisect each other. They cut each other in halves. So this stick right here is equal to this stick. This stick is equal to that stick. That's still true. If you're looking at your little steps there, I do have that in there. Right? That the diagonals still bisect each other. It was theorem 6-7. Well, how many marks do I have in each of these triangles now? 3. And if you're actually looking at your little proof that I have on the actual PowerPoint here, it actually says side, angle, side. Right? SAS. That's actually the reason why all 4 of these triangles are actually equal to each other. They have all the same markings. So it forces all 4 triangles to be equal, And if all four triangles are equal, then everything about them is the same. So they're all congruent parts. Namely, these parts have to be equal. And that's the whole proof. And that's the steps you're actually looking at on your slide. Now, if you want to write down the full-on proof, go ahead, fine and dandy. I'll have it on the website tonight once I update it. But I want to show you, like in front of you what it is, but if some of you like to see it in words, I have it typed out for you in case you want to see it. Questions on how I actually prove that all four walls are the same, so it forces it to be a rhombus by definition. I had to prove that all four triangles are equal, and then it forced the walls to be the same. Are we going to 617?
I'm almost done right now.
Okay, that's fine. Okay, we'll probably get one more theorem today, and that'll be it. We'll stop at after the next one. And again, all the steps are there in case you want to write down the whole on proof.
Yeah, I'm good.
Okay. Is everyone else good?
No.
Okay, let's go to 618 now. Okay, this will be our last one today. 618. Ooh, I better get rid of my marks. Forgot all about those. Alright, 618, it's showing up and again on yours. I have all the steps written out, so you can actually see it. Question.
What was the name of the last one?
Oh, good question. Good question. It was the converse of 615. Ooh. Converse of 615. That was the last one, by the way. Converse means you're flipping the words around. You know, 615 talks about if you had a rhombus, then the diagonals are perpendicular. This one talks about if the diagonals are perpendicular, then it's a rhombus. It flipped it. So it's the converse of 615. All right, but 618. Okay, this one talks about if the diagonals bisect the opposite angles in the corners. So on this picture, we're given that this picture is a parallelogram. So we have certain walls are parallel, and certain angles are bisected. So angles 1 and 2, 3 and 4 are bisected. This angle and this angle are bisected, like that. Bisects the opposite angles. Then this picture has to be a rhombus in the end. Okay, so now what I mean by that is I have to prove that all four of these walls again are equal. Now if you're looking at the proof on your actual slide that you're looking at in your Nearpod, it explains it all in words. But one way to do this, so now if you're looking at the picture, I bisected the angles in the corners, namely certain angles are equal to each other, because we know that opposite angles are equal. And it forces, in this case, the triangles to be equal, because watch how this works. So I have all the angles marked as the bisector, that was the check one. Okay, so the angles are all bisected, so opposite angles are equal. But we know, and this is going to seem a little goofy, since this is a parallelogram, that the diagonals are also bisected. So we could even go with the vertical angles. The third angles are equal. I know that's different than what you might see in yours, but I could go this route where the third angles, that's one route you could go. I'm not necessarily saying that you have to. I could go with the route that the opposite walls have to be the same, because it is still a parallelogram. But I could force certain triangles to be equal to each other, because of the way that this works by angle side angle. And once I have certain angles forced to be the same, then I could show that certain triangles are actually equal to each other. We know the diagonals still bisect each other, and I could go that route. However you want to go with this, because there's multiple ways of doing this. I showed you one style of proof in your notes, and here's all the steps that you had. You can make angles 1 and 2 all equal. The fact that angles 1 and 4 are equal, that alternate interiors, allows certain sticks to be the same by reflexive property. And so I'm actually showing you that the whole top triangle is equal to the whole bottom one, because if there's certain walls and certain angles. and then it forces the opposite walls to be the same, and it would force the issue and make it a parallelogram. And it forces it to be isosceles, so it forces two walls to be the same. These two. So there's multiple ways of doing it. What I was showing up here is I can force certain triangles to be equal. And then once I have certain triangles being equal, I can show that the angles in the middles have to be 90s, and that's one way I could prove it. But the way that your the book has it, this is the book description, they go with the whole isosceles triangle idea, where they actually, instead of going after all four, they go after the big triangles, these. They go after the big ones, and then they talk about that these are isosceles, so it forces the two legs to be the same. And then all four walls are the same. So there's multiple ways of actually proving this one. I just showed you one. I thought that was kind of a cool one, going isosceles triangle route. But very, very different. But again, the name of this one, by the way, if you don't have it written down, this is the last one today. It is the converse of 616. Now it's the last one we're going to end with today. Now tomorrow, we have two more. We'll do a couple example problems, and then we're going to do a little activity tomorrow, which I think you're going to like. It's a little bit different than what we've done in the previous past. Okay? Alright, that's it. Let me disconnect your near pod here.
Mr. Wade,
Yes.
can I leave class early so I can go to the bathroom? So I'm specifically done my first thing 4 times a day.
Yes.
Thank you.
Oh, you're supposed to not get automatic. Click on it. Hey, Ward, do you want the light on or off?
Let's go on.